Thank you, Catherine. So you nicely summarized what you're going to talk about. So let's not make a delay and let's see who we are. So I'm Arnab. I'm working as a data scientist with the mobility team since last year. And here with me I have Florian, who's also working as a data scientist from Inovex, which is an external consultant. Also on the similar problems on the topics. Just to get you a feeling what's going to come up in the next half an hour. We're going to talk about a motivating example. We want to show you who we are and what actually drives us to make this kind of decisions or data-driven solutions for the car market in particular. We're going to see some theories, some background theories, which going to help us or design such systems in the long run. In particular, since it's a Python conference, I would like to pull up actual production example, how you show, where you show how you bring in all the algorithms and Python in one nice pipeline. And finally, Florian is going to take a deeper look into what can be done from now on. So talking about who we are Mobility. We are part of eBay Tech. eBay Tech consists of several other entities across the globe, and Mobility is one of the major ones who are much prominent in the German car market. So we are like a marketplace for vehicles, includes bikes, trucks, or even four-wheelers for common man. Just to give you some numbers, 13.5 million unique users every month, and almost 1.6 million vehicles, including, as I said, and we are located in Dreilinden and also in Friedrichshain, which is a motor talk office where we have two major offices and almost 290 employees. And over to Florian.
Yeah, so Inovex is an IT project house for digital transformation. And we are supporting Mobile in fields such as big data engineering and data science. And our offices are located in Karlsruhe, Munich, Hamburg, and Cologne and Pforzheim. So, wait a second. This went on, oh, sorry. So, yeah, our actual topic is why recommendations. And if you imagine you would walk into a normal store, this example, we chose some bag store, you want to buy something, and you're not only seeing what you're looking for, whatever you have in your mind, but you're seeing the whole width of an offering. And by this, it might be happen that you go into a store and you actually come out with a product that you would never have even known that it existed before. So you get inspired by other products, you see the whole offering, and you are able to engage with the product. And the same thing is actually something that you want to achieve if you have some online marketplace, right? But there, things are a little bit more difficult, so you have way more products. And in our case, in the case of Mobile, I mean, there are 1.6 million used cars and new cars online at the same time, but actually we want to achieve the same thing. So we want to be able to inspire users that maybe don't know exactly for what kind of cars they're looking to engage with new cars, and actually to find then the perfect car for their life. So this is something where recommendations can help us. So we see on the one hand, we have the user benefits in the sense of more engagement, you get inspired, you get presented relevant articles, relevant cars, and at the same time, it's also always the other side. So you have some business benefits like higher click-through rates and smaller exit and bounce rates. You may all have heard about the conversion funnel. Yeah, thank you, but yeah, we would take questions later, thanks. So you might have heard about the conversion funnel, which means basically when you have the intention, in our case now, to buy a car, you are basically starting on the mobile homepage. So at the first stage, and then the last stage would of course be you buying the car. And in between, you move through different stages, like you get a better idea, you search, you view, you might park cars. This is a kind of our wish list, so you can favorite cars and put them on your wish list. And in each of those of these different stages, of course, you could also drop out, and we want to support users and inspire them to find to get new inspiration and engagement at every stage. So to actually show you something how this looks like, so for instance, this is the home, the first page of Mobile, and there, for instance, recommendations could support you by giving you not only what we have on the upper part, like some search mask, but also like for returning visitors based on their user preferences, like what cars could you be interested in, from what depending on the preferences what we know about you, and also where you left off. So the next thing, if you had now like searched for a car, you get presented a search result page, and also at that stage you actually or we actually can support you. Let's assume in this case you looked for an Audi A4, and you might not know that a model like the BMW 3 is something really similar. And in this case, one could say, hey, there's an alternative cars. Alternative model? Have you looked into these kinds of models? They might also suit you well. Then also, if you now like the car, if you put the car on your wish list, then if you viewed the car, so you clicked on the car, if you view the car, then recommendations can support you by showing you similar cars. So cars that have the same attributes, and also depending on your preferences to inspire you to also look other cars, because there might be certain aspects that you don't like about the car that you just viewed. If you now viewed the car, and if you like it, you could, for instance, put it on your wish list, and based on the wish list, we then also can propose and do propose new cars based on the preferences, because this is a high feedback of the cars that you like, and this can also be used can also be used to give you recommendations. So we see that throughout the conversion funnel, we can use and can apply recommendation to make the user experience better, and then to go into the later stages like contact and buying.
Exactly, to have such awesome product, you actually need to see what awesome things are behind the scenes. So I would actually brief you up here to show how things are actually working together. So the first thing, just to give a primer, like this is not going to be like a recommender 101 session. So we would like to show you how the traditional algorithms can fit into our domain or our problem set. So let's start with the common one. How many of you have heard of collaborative filtering? Awesome. I can skip this. Okay. So let's see how it happens. Let's say we have a car in our database, and we have a lot of users, as you saw, like over 13.5 million users. They kind of liked or parked, as Florian said. They interacted in different ways with this car. And that's you, who also liked or viewed this car. Pretty nice. Now, this set of users who are interacting, or who interacted before with the system, for instance, this set of people, they also probably like this other car. So it's another different car. And now what the system smartly does is kinds of finds a degree of similarity between these two based on the commonness or the common interest shared across a lot of people. And it's pretty simple from now on. You easily just recommend this car to you. And that's exactly how collaborative works, bringing in the collective intelligence of your users. Now let's see a bit more detailed example how we actually use it on our case. Here you see some movies. Definitely we're not dealing with movies, but that's a common example we pull up because you guys might have seen this common user movie example from n number of sources. So you have Star Wars, like top 2 movies, and you have Notting Hill. and people rated this in such fashion. And you can immediately see here that from the way people have interacted with these movies, you can define, if you can see the dot, okay, this Star Wars and the Empire Strikes Back, a lot of people have put a kind of similar ratings, or like have a common users who have similarly interacted with these movies. Whereas Notting Hill has not been rated similar way. Now, given this kind of a matrix, which is like user versus item, we can come up with different kinds of similarity definitions. What's important in this scenario is we are never looking into the content of those particular items. As I mentioned shortly, like the concept of similarity, and simple could be cosine one, could be a Euclidean one, or anything else depending upon your use case. Now, we don't have movies, we don't have Star Wars, but we have awesome cars. That's how it looks. We don't rate cars, also to keep in mind. We are not explicitly rating 2 or 3 to our cars. What we are doing is we have different levels of interaction. This means that he viewed the car, which Florian said, so he just viewed it. Then it could be a parking, or like a wish list, which is like he set it as favorite. And then is this mail sign, that means he contacted a dealer. So these are the different degrees of likelihoodness, let's say, that a user can express with an item. So you can actually rate it and say like, okay, it could be 2, 3, 5, could be 1, 2, 3. This is not written in stone, so you can actually have any kind of rating here. Once you have that matrix looks super familiar, because right now you just have that user and movie matrix. Once you know that, it's extremely easy to look into what you have parked or what you have wishlisted, and then give you a nice recommendation. So to summarize it up, like what this whole concept of collaborative filtering is, it definitely looks into the collective behavior of people. It's a very nice method. You don't need to dig into the content. You can have it works really nice as a baseline, or you can just plug it and play it. It will work really nice. What's the problem? Cold start problem. How many of you have heard of the cold start problem? Okay. So definitely, what you see is there has to be a degree of interaction. Could be a user cold start, that means a new user comes to the system, or could be an item cold start, like a new item is listed. Now, the second one seems most serious, because we can have a new Audi Quattro model released, and we'd really want that model to be recommended to users, otherwise people will not buy it. But nobody interacted with it. How do you solve that? So that's a classical item cold start problem. So you don't have interactions, but to make this thing work, you need interactions with the items from the users. Second is sparsity problem. Like when I showed you the matrix, you have almost millions of users, around 10.5, and like we have 1.6 million items. And everybody never interacts with all items, and all items are not rated or like viewed by all the people. So you have extremely fewer data points in that 2D matrix, what you actually is possible in theory. So that makes the matrix extremely sparse, and given such a sparse matrix, to compute any kind of similarity would give you near zero results or near zero similarity values, so which is really not helpful. We'll show you how we circumvent this problem. Second, it's a batch-based learning, because you cannot just have a new row inserted into the thing and you can just do any incremental learning. You have to pull that whole matrix in memory, recompute whatever learning methodologies you're employing. So pretty resource and CPU intensive. Okay, can we do something else? Definitely. Before that, I will actually introduce a concept of user preference. So a user preference is basically finding a behavioral pattern of a visiting user. And that's totally an anonymous sense. So we really don't know even if Florian is logging in just beside me, I cannot say like, okay, it's Florian's data. It's totally anonymized. So there is no ID, nothing PII information there. And how does that particular profile look like? You have his preference over the variety of cars he has visited. For instance, BMW, he's more 50% Audi, so it's like a split it equally, to give you a simple example. For example, in models, he's more into A3 and A4. So as you see, like you can define a fingerprint of that user, like, okay, that's his behavior, that's his browsing pattern. How does it help us in content-based filtering? How does content-based filtering work? You have the same car. Now the difference is we have all the features of the car here. As I've written here, it's a price 10K, extremely simple vector. Ideally, it's like could be a very long vector of all the attributes possibly you can think of. It's a small car. Now, you as a user interacted with this car. Just now we talked about user preferences. So the moment you interact with this kind of a vehicle, the system knows like, okay, this guy has that kind of a profile because he likes 10K car and he likes small cars. So you just kind of copy paste the user, like his behavior, like the car attributes into his behavior. Now let's say we have 2 more cars into our database. Like one is a mid-range, like a low-range car, 6K. Another one is a high-end Porsche maybe, high-end sports car. They also have their attributes. Now once you have this kind of a vector of the user preference and you have the vector representation of the car features, guess what? It's super simple. You can actually compute any similarity matrix on these 2. And once you have that, you can say like, okay, you just recommend this car, but not this car, because this guy is more similar to his interest. And that's the whole concept of content-based filtering. How is it nice? Even if you're the only user in the whole system, we still have recommendations for you. You don't need to have a collective intelligence of all the other people who are there or not there. We don't care about that. As I said, it's like you learn from the preferences, you learn from how he interacted, we build a preference. And as we see like he interacts more and more, this vector or the preference vector gets updated. So that's a different problem altogether. So that's like building his preference vector. Also, it's a bit difficult for new users. For new users, we have a totally different approach of users to tackle user cold start problem. However, it helps with the item cold start because the moment you have Audi Quattro, which is released in the market, you know its features, and if somebody likes it, you can recommend that car. So it was missing in collaborative before. This is a general statement, non-applicable for heterogeneous items because content-based, since it looks into the feature vectors, let's say you're dealing with DVDs, it's difficult to recommend a cricket bat or maybe a football to somebody because the content essentially is not the same, so you have to have analogous item set. However, we do not have this problem seriously because we are dealing with cars, lucky us. The bad thing about content-based is like low diversity because once you have a vector, end of the day it's a vector similarity, so you kind of end up with similar kinds of vehicles, so you don't, because with any standard recommendation engine, it's highly recommended that you should have a nice diversity so that people see different kinds of things but still aligned to his interest. So that's pretty much missing in content-based. Okay, so those were the 2 ends of the spectrum. What can be done? Something better? Definitely.
Yeah, so now we have heard about 2 approaches to recommendations, and in this section we show how we combine them to make up for the use cases that we showed. So again, to our actual goal, finding the perfect car. I mean, for her it's quite easy. So for firefighter, it's just a fire truck. And okay, so what kind of data do we have? So we have heard about the preferences of a user about the car. So this is more than the content-based part. We also have, on the other hand, the interactions of other users. So this would be then the collaborative part. And we also, of course, have all the attributes from our car pool, so the millions of cars on the site. And additionally, we have some certain requirements. These needs to be, so the recommendation needs to be really flexible. We heard and learned about the cold start problem, and this is something we want to avoid because a used car is not like you have many of them, so you have this one single used car, and they, after the car is bought, it's no longer available, so the inventory changes quite fast, so the cold start problem is actually quite hard. Then we deal with a certain kind of uncertainty about user preferences, for instance, about new user, and of course also like real-time issues. You want to learn the preferences also really fast when a user interacts with the website, because buying a car is like more like a one-time thing, and then you might return only like after 2 years when you want to buy a next car, and your actual preferences might have changed completely. So what we did is we combined the different approaches into a hybrid approach, into a hybrid recommender, and this in order to avoid the cold start problem, to deal with the new users and new cars in real time. And the good thing about this is, since it's a combination of two default and reliable methods, the hybrid is also a robust and reliable concept. It's also easy to tune for the different use cases we have. So we have seen the different use cases, and if you, for instance, want some use case to be more collaborative, you could put more emphasis on this part and less on that part. So it's easy to tune. And it's also, what's a big plus in production, is also comprehensible and debuggable, yet, for instance, compared to deep learning, which we'll later also go into. So how does the architecture look like? So imagine you're a user, you're coming to the mobile website, then a certain your user preferences are loaded, and at the same time all your interactions, so the right part, are also tracked and stored to basically update your preferences. So that's if you click on many red cars, for instance, then one knows, okay, there's a certain affinity for red cars. Then these user preferences are also used in the recommendation engine, which then uses collaborative aspects from Mahout and your user preferences combined together to query Elasticsearch with all the listings to finally then, in the end, give you the recommendations. And there are different technologies used in this. So it's just that the Mahout is used then for the recommendation engine is a combination of Python and Java. And over here we have a lot of the Hadoop stack with Cassandra and Kafka and so on. So how is now the recommendation done? So basically the two informations we have, so the collaborative part, which gives us a similarity between the different items, between the different vehicles, and the user preferences are used to create a query, which is optimized based on a ROC-AUG score. And then what the practical scoring function of Elasticsearch gives you is a sorted list of different scores, and then you can basically use the top n results from this query to show to the user as recommendations. And for one of these aspects, we will see an example.
Exactly. So right now I would go through a real example, what we had to develop. So the task I was given was to find similar make models. I mean, because we found out like users often in their orientation phase, they're not sure like what they type something, they look for something, but that's not it. Like you might, or you should give the users a lot of other options, like, hey, not just that, also consider looking into this kind of cars. So that's where the whole concept of similar make models. So make could, just to give you a brief, make is like BMW, Audi, Volkswagen. Model could be A4, A3, Quattro. So these are like just the terminology. So the idea here is we have to find them, look into those similar models as far as possible, so that they can have a more informed decision. And in order to do that, we go through an example of a collaborative filtering here. And this is not an example of a hybrid one, but just to show you like how Python and the data and the whole matrix interactions come together in one nice form. So a user looks for Audi A4, just to repeat myself, like it could be like we would be suggesting some similar vehicles like BM645. Talking of Python, what we used under the hood was LightFM, an extremely nice, well-documented library for doing all kinds of recommendation jobs, which includes implicit feedback or explicit feedback, which I didn't mention yet, but people who are familiar might take a deeper look. They have very nice documentation, and the nice thing is It has a C compiler, so it's really underlying, it's like almost C-like speed, so which is really optimized for your hardware. And the awesome part was it's like using all your cores, so you can actually have a high number of threads spawned, and you can actually train models or like data set in parallel. Also, there are like a lot of objective functions to choose from. For instance, here, like Bayesian PageRank or like weighted approximate ranking. These are more suited for scenarios where you have just positive rankings, like 1, 2, 3, as we showed. You can also have logistic, where you have plus minus, like thumbs up, thumbs down kind of data set. So you have a lot to choose from. So how does LightFM and cars and items work? Don't be nervous. This is I wanted to make it super simple. So we have a data set, the same data set, the data matrix I pulled from. So you have millions and millions of users here, 10.5, let's say, and you have like almost 2 million items here, and people have rated everything in a different fashion. Let's call the matrix M, which is like cardinality U, that means like number of users in your data set, and cardinality I means the number of items you have. So it's basically, think like 3x2 matrix. The idea is, we should be splitting this matrix in two components, like one left one and another is the right one. Why? This matrix on the left-hand side, M, is extremely sparse. We have extremely less data points. And as I mentioned sometimes back, I'm repeating, if you try to compute any kind of similarities, you can say like, hey, we don't need some sophisticated methods like this. You can just look into the columns from this left matrix, like through the columns, and you can just compute similarity. But again, like you have so less data points, you will end up with near zero similarities. Number one. Number two, these interactions, these collaborative interactions are really lost when you see such extremely sparse. So coming back to the age-old problem, curse of dimensionality. So it's so huge a dimension that all the real information is just lost there. What we do, break it up into a left and right matrix, into two intermediate, or let's say latent factors, or like latent features, which I call LF1 and 2. So that means you just split into two components, so like latent feature 1, latent feature 2. What's the problem is we are trying to find similar vehicles. So what's important here is this R matrix here, if you can see the red dot. So the R matrix is the most important one, because what you see here, the whole sparse data matrix has been transformed into a super compressed, having the same information content, but better represented, and it's like considering all the collaborative aspect of it. Once you can look into those columns, which are called item embeddings. Today in the keynote also, she mentioned about embedding. So it's nothing new here. So it's a representation of an item in an extremely high dimensional space where it is like nicely defined. Once you have two vectors, that's it. That's the job where LightFM ends, and you don't need to do anything. You can employ any state of the art. Even with NumPy, you can just do some vector similarity on top of it and come up with a score. And what you see on the right-hand side is, like, so we have all these make model combinations. So we define every make model as one item, and we see like, okay, how did they interact with this? And what you end up is like this n cross n matrix, or like a similarity diagram. So if you have, let's say, 10 make models, so each model compared with itself. So the diagonal here would be like, if you can see, it's a white line. That means like similarity 1. So it's like same comparison, like I'm compared with myself. So that's the diagonal, and like the others are, the lighter ones are the high similarity zones, the darker ones are the bad ones. That's it. That's all you want. You want to have similar make models. So if you can look for, you just take one row, which is represent an item, you can give me like the top K ranks of all the similar items. That's it. Just to give you a sneak peek how simple it is. Can you read the left-hand side? Okay. The left-hand side is basically how the LightFM is used. Just 2 lines of code, literally 2 lines of code. You just define your loss function, as I mentioned, some item alpha, which is like the regularization you want to employ, and the number of components, the most important thing, the number of latent feature variables you want to blow up on. I mean, like you have the whole left matrix M, so you say 3, 4, 20, 100, 1000, whatever. But keep in mind, it should be less than the number of items, otherwise you're not gaining anything. And after that, you just say model.fit, like similar to any other standard machine learning algorithm. You have a model, fit it with the data, you see matrix, And that's it. You see epochs, which is like number of data passes you need to make, and the degree of parallelism you want to have, like how many threads you can do. And on the right-hand side, it's a snapshot of our MongoDB where we build this model overnight, and you save this top case similarity. So the top is the query item, BM645, which is like defining the make model, and you say like with a score, what's the similar ranked accordingly on the score. So you have this one, this comes up next, then this, which is pretty awesome because the guy looked for BMW, and we also proposed him Audi and Mercedes-Benz CLA, which is like pretty similar models. So to sum it up, we saw the two ends of the spectrum. We saw a hybrid approach. So what does hybrid help? So it basically tackles three main areas. The method is like best of both the worlds. We just saw how we combine both of them. Second, the user gets a bit of engagement. He sees a lot of diverse items when he visits on each of the funnel steps. Also for the business, it also results in higher click-through rates and like lesser exits through the funnel. And let's see what we can do even further.
Sorry. Yeah, so besides this, we are also looking, of course, into the new cool stuff. And in the morning already, we learned about deep learning and how it is applied in natural language processing. There are many other cases, cool use cases for deep learning, like for instance, finding skin cancer, or there's a paper about a poker bot that beats most humans when playing, and you all have heard about AlphaGo, which beat the best masters of Go. And I mean, what are the reasons then? I mean, of course, there's the hype about deep learning, but the actual reason one applies deep learning is that it helps to capture nonlinear relations. It's also some kind of holistic approach, which is also a nice aspect. We have seen that in this hybrid recommender, we are basically combining two components, and there's different optimization in each part. And with deep learning, you are basically applying one optimization on a whole, on a whole structure. And it's also less feature engineering. And this is also some of the big advantages that people are always saying when referring to deep learning, that you have way less to feature engineering to do, because basically the network, the different layer helps you to do it. And of course, we expect also to have some improved quality. So this is kind of the stuff that we are looking into right now. There are no final results. So what we are applying is, just to give you a small overview, is Google's wide and deep learning model, which is also used in Google Play. Okay, which is, I speed up a little bit. So I'll directly then show the whole network, just to give you an overview. And so basically, we still have the features, of course. We need to do some encoding for the continuous and the categorical features. And then we have basically two parts. This is why it's called wide and deep model. And the wide part, which is on the lower, what it basically does, it helps to memorize really specific things that you like. For instance, if you like this one Porsche 911, so this would be the layer that is really understands that you're in this Porsche 911. And then there's the deep components, which uses embeddings. We've heard about the embeddings, and different layers which generalize more. So this part of the network would then capture the fact that you're, for instance, looking for a family-suitable car, because the whole time you were looking for large cars which are really safe and so on. And these are, in the end, combined to give you a probability that a user X likes a vehicle Y. So to sum this up with recommendations, we support the user to find the perfect vehicle based on the preferences and and collaboration aspects. Thank you very much, and do we have any questions?
Excellent, thank you. That was a wonderful talk. So if you could raise your hand if you have a question, and Jeffrey will come to you. I think we'll start there, as you were the first hand up, and then we'll move in. We have about 6 or 7 minutes, and then of course you can find them. They will be walking around the conference if we can't take your question this time.
There's also a booth outside. Yeah.
Thanks for the talk. So since you are using a hybrid method between content-based and collaborative, have you considered using factorisation machines?
Yeah, in a way, with Light FM, we are using a factorisation machine method. So, I mean...
May I ask you then later a bit about details? Okay, thanks.
I wonder, how often do you update, I guess, the features per user, per car?
So the feature per user are directly updated as the tracking goes in. So it's not really directly real time, but like depending on the Kafka, like in 5 minutes window, it's updated. And the car, I think they are almost directly updated. So if a dealer like changes the price, for instance, then it ends up in the ElasticSearch, also in a really short period of time, and then this is then used in the next recommendations. Is the updated price used?
There's this saying in Germany that people like to look at high-end cars, but their budget dictates smaller cars. Does that bias the recommendations, and how do you deal with it?
So I can tell that. So yes, definitely you're right, but that's the power of collaborative, I would say. Like if you just look into a lot of users, that contributes to really a low segment of people, and when you really want to find a similar one, they should have a similar behavior, and that's very intrinsic within this whole collaborative metric. So you really don't need to bother about. However, you're pretty right. We have other projects which are coming, like we are taking care of, which is like defining those kind of users who have those particular behavior. So we can see like, oh, okay, this guy is just a surfer, so weigh him differently.
Yeah, you're definitely right, exactly. So as Arnab has said, so you can kind of already see that there's even no buying intent then for those cars, for those people. So they just like to watch those cars but have no buying intent. And then if you can separate them and do the recommendation based on the remaining ones that have a buying intent, then you can help to improve this, that you don't have the bias.
So my question was about how you put all this in production, and actually, did you find any limitation with the library that you are using with Light FM? For example, can you fit the whole model in memory in the GPU you are using? Are you using
yes, definitely
many GPUs? So
it is resource intensive. So the secret is there is this sparse matrix representation in Python where you can just load this whole data and it just has extremely dense representation of it, and then you can use that. So the matrix to use the matrix you saw in the code line where you fit the Light FM model. That's actually an extremely condensed representation of the matrix, and that easily fits. So we had like a 32 GB RAM machine, so it just takes around 6 GBs of RAM. I think it's doable. I mean, like for the moment.
Not directly related to the methodology, but did you find interesting or funny correlation between the users and the cars?
What do you mean, like model specific or? Yes, people, like we found like Volkswagen is definitely one of the most popular brands people actually view, but they end up buying something else, often which is like Opel or maybe Ford or something. So there is quite a variance in the different stages of the events. When Florian said he views it, he searches it, he parks it. So on different levels, there is a different diagram of the interaction. So is that what you wanted to know?
Yeah, okay, but more related to the user's profile. Is there interesting correlation between the user profile and the cars they are looking at?
It's not really.
I mean, it's just an
profile
anecdotal question.
I mean, since the preferences, I mean, they're constructed by what you actually look at, and then therefore you kind of implicitly have a strong relation. So, I mean, there's not like external data used. I don't know. So it's not like a profile in this sense. It's more like about your preferences. Or is this what you mean? I mean, it's not. I mean, how would we, for instance, know, for instance, things like your income or your age or whatever? I mean, this is not something you give to the site, and this is no information we can then directly use. So it's not a profile. It's more like a preferences based on your journeys on the website. If this is what you mean, because yeah, there's like no way of saying, okay. Like people over 50 years, but this is information we don't have, right? So it's not like people are saying, I'm that old, I'm a man, I'm a woman, or something. So, so it's more like a preference. It's not like really a profile or something that's, for instance, Facebook would have, right? Facebook would know a lot more,
So no PII information.
Yeah, there's actually no PII information used. Yeah.
Okay, we have one quick last question, and then of course Florian and Arnab are here, so please find them and ask them more questions. I love that there's so many.
I was just a little surprised by an answer you gave earlier, because you said you can recompute recommendations almost real time, but clearly you weren't talking about the collaborative filtering part where you're decomposing the large matrix into a user matrix and a item matrix. So how often does that part get recomputed?
So the pipeline or the requirement there was like we have to come up with the similar data. So all we needed was to have a list of similar items. So we train it once a week because we assume like, okay, the behavior doesn't change so often. Definitely it changes. And once we have it in a database, we can just serve them image. So we have a Scala service there. So whoever, hey, what's the most similar car with model ID X, it can return you the top key result. So that's one part of it. And as Florian said, the user profile update, it's like more real time. And we also have a batch component. So it's extremely complicated under the hoods because there are a lot of machineries working together. So definitely I'm happy to talk about it offline.
Yeah, and this is actually exactly the key point with using then also content-based versus collaborative, because you're right, with collaborative you would need, if you have a new car, you would have to retrain because you just see the number of the car in a way, right? It's just an item, a complete entity for you. And this, of course, one cannot do so often. But on the other side of the content base, so if you have the features of the car and the preferences which you can easily update in real time, you can make up for this. And yeah, this is how it's done.
Excellent. Can we give another round of applause to the great speaker?